Alright, so we started to look at binomial expansions and how Pascal's triangle plays a part in that. This is going to lead into what we call the binomial theorem. And to kick this off, we are going to expand x plus 3 raised to the fifth. So we're looking at something a little more complicated than just an a plus b. Alright, so we're looking at x plus 3 to the fifth. Keep in mind that this 5 is our n. And if the n value is 5, we said that there are going to be 6 total terms. Remember that if n is 5, yes, it's the power of the binomial, but it's also going to be the fifth row in Pascal's triangle. Now this is a reasonably small number, so it wouldn't be too terribly time consuming to construct Pascal's triangle. Oh, my son is crying because it's bath time. Oh well. So take a moment here and create your Pascal's triangle. I sure hope you guys don't cry like that when it's bath time. Ay, ay, ay. Anyway, so we are looking at finding our 6 total terms. So I'm just going to put 6 little placeholders here to represent our 6 terms. Okay? So we know that finding the 6 terms in Pascal's triangle is not that tedious. However, if this binomial had a power of, let's say, 10, you would not want to go all the way to the 10th row. So you want to be aware of how to use and choose R to get these different values. Okay, we'll write it out here, okay, but we know the numbers are already right here for us. So I'm going to use vector notation to do this. So since my n is 5, my first term would be 5 choose 0. And again, that would give us this 1. The next term, 5 choose 1, would give us that 5. Then we have 5 choose 2, that's the 10, and so on. 5 choose 3, 5 choose 4, and 5 choose 5. Okay? Then we have to look at our first term in this binomial. It's an x, and we said how it is going to get raised up to the power of n, which in this case is 5. And I'm going to just keep this all in parentheses here. Okay, parentheses are important, especially if, suppose this were 2x plus 3. All right, and you'd have to raise that whole quantity 2x to the fifth. Then it's really important to apply the power to both parts. Here it's not a big deal, but recall how we said the powers are going to go down by 1 each time. And the last one here, that's really x to the 0, but we don't have to write it if you don't want to. It's really just going to give you 1. And what's the matter? I hope you find all these interruptions amusing. I know I certainly do. So next up here we have our 3. So this 3, the last part of the binomial, is going to be raised up to the power of 0, and then it's going to go up by 1. Keep in mind all these parts are being multiplied together. Okay, so it's one big cluster of multiplication. So the last one would be 3 to the fifth. So from this point, we want to just very carefully go through and clean this all up. All right, so again, what I have here in black, these just all correspond to the numbers in Pascal's triangle. So if we were to expand this out, so here we would have our complete expansion showing the 6 terms, okay, in this expansion of x plus 3 to the fifth. Okay, last example. Here's a more complicated one where, again, we're looking to expand this. Now the power is just 3, so that means we want the third row of Pascal's triangle. Again, this number is small enough where we can just use Pascal's triangle. So there's going to be 4 total terms. So I'm just going to write out these placeholders here. And if it's the third row in Pascal's triangle, that's going to correspond to the 1, 3, 3, 1 row. So I'm just going to write out 1, 3, 3, and 1. Okay, I won't bother with the NCR notation. Okay, so here's where it gets a little more complicated. So now we have this 3x squared. That is our first term. That is going to get raised to the power of 3. And then we're going to have 3x squared raised to the power of 2. Hopefully you can see why it's important to include parentheses, right? Without the parentheses, we're not applying the power to each part. And then our last term here is negative 2 over x. That negative goes with it. Okay, so that starts at 0 and then goes up by 1. Okay, so notice how I'm using parentheses just to group this all together. Okay, all right. So the most challenging part now for people is simplifying all this. So right here, you have to understand that we need to distribute this power of 3. So of course 3 cubed is not 9, it's 27. So we have 27. Then we have a power to a power, so that's going to be x to the 6. All right, and that's just going to be 1. All right, and then we have, all right, just attack this very carefully. Okay, we have that 3. Then we're going to have to square these parts, so you're going to have 9x to the 4th, and then times this negative 2 over x. It's just raised to a power of 1, so that's not going to change it at all. Well, that's going to give us a minus 54, and then this x to the 4th is going to be divided by an x, really to the 1st, and so that's going to become x to the 3rd. Okay, so of course when we divide and they have the same base, we subtract our powers. So our next term here, we have a 3 times a 3x squared, and then this is going to end up being times a 4 over x squared. So you're going to have to distribute this power of 2 to each part of the fraction. So when we do that, notice how the x squares will divide each other out. We're just going to be left with plus a 36. Okay? And pay attention here too to the powers of x. Notice how it's going down by 3. Technically you have an x to the 0 here, but we don't have to write that. So we can predict that this next one is going to have an x to the negative 3 because it's going to follow that pattern. Okay. So as we look at this, this is raised to the 0, so that's just going to be a 1. Here we're going to have to distribute our power of 3. So we're going to have a negative 8, right? Because negative 2 cubed is negative 8 all over x cubed. You can write it like that, or you can write it as negative 8x to the negative 3. And again, that shows how the powers of x are going down by 3. So the 4 terms in our expansion would be what we see there. Okay. So last thing here, you'll notice in your formula packet that you have a binomial theorem formula given to you, and it shows that when we have the expansion a plus b to the n, it's given us the individual terms here in the expansion. It's essentially showing you the pattern here and how our first term here has n choose 0 for its coefficient. It starts with an a to the n and a b to the 0. We've talked about how the a power goes down by 1 and the b power goes up by 1. Okay. The very last term here, you would see n choose n, so something like 4 choose 4. We talked about how the last term here, the a would have a power of 0 and the b would have a power of whatever n is. Okay, so that's that basic pattern. You'll also see this written as n choose r, and then a raised to the n minus r times b to the r. That'll summarize all of these terms here. Remember we said that r is 1 less than the term you want. So if we're talking about the first term, notice how the r is 0. Okay, and notice how the power here, n minus r. Okay, so if I were to look at this right here for my first term, all right, n minus 0 would just give me n, and then the b power is always r. Okay, so this is really what we mean by the binomial theorem. Alright, so this is what we are going to use to find a specific term. It's actually pretty rare for you to have to expand out the entire thing. We don't usually want the entire expansion. We might be interested in just a specific term, such as the fourth term. Alright, so we are going to use this formula for the binomial theorem to help us to find specific terms of interest. We'll see that in the next video.